Welcome to Module 1, Part 2. In this part, we're going to be talking about network sharing and packet switching details. So one thing that needs to be kind of dealt with networking is effectively sharing of links between multiple different users. And so there are two major approaches that exist in this universe. So one approach is circuit switching, and the other major approach is packet switching. So the circuit switching is what we used to have with the old telephony, and effectively what it does, it sets up a literally route between 2 points. Not route, like the actual path between two nodes. And if I try to illustrate here is on a slide, is effectively when we trying to set up some kind of a call, there is actual physical switches being kind of created between each points of this network, and we're creating some kind of dedicated line between two machines. So it's an interesting approach. It's a kind of workable approach. We had it for many years. But the problem is that you have to dedicate this link entirely to that one user. And of course, there's also cost to set up this circuit. But the problem is, the major problem is the guaranteed kind of allocation for that specific user. Even that user may not be using that connection for or like that circuit all the time. But you guarantee performance, but again, potentially you waste a lot of capacity. This may not be that a big deal for the old calls, because you cannot really call somebody, share the same line for the calling purposes, because you can hear somebody else and you cannot have multiple conversations. But for the data sharing, it's a completely different picture. So when packet switching was invented, it actually changed the picture considerably. So you no longer require having a dedicated line, and all switching is done per packet basis. So you kind of the only kind of thing that can be allocated, but in this case is not even allocated anymore, is the packet. You kind of present this packet to individual machine. That machine decides whether to allocate resource for this packet, and then trying to send it to the next machine, to the next router. And afterwards, the router again taking the packet, decides whether it can forward the packet, and then trying to forward the packet further towards whatever destination is kind of specified in the packet. So this is kind of the core fundamental part of the packet switching. But just to give you additional ideas of the whole picture of telecommunication networks, so kind of you can consider them, as already mentioned, as a packet switch networks and circuit switch networks. And within the circuit switch networks, you can kind of think of FDM, or frequency division multiplex, and TDM, time division multiplex. I will talk about them in a few more slides. And for the packet switch networking, we have virtual circuit networks. So it's kind of trying to emulate the elements of the circuit switch networks, but rather using the elements of the packet switching. So it's kind of hybrid between two types of networking. And finally, there's a datagram networking networks. This is what effectively we're using right now. Okay, so let us talk about what is this circuit switching, and what FDM and what TDM are. So, for example, let's take kind of this small picture. Let's kind of take example of FDM, or frequency division multiplex, and we need to see what we can do with this kind of media in frequency/time domain. And the assumption here is, kind of, if I get back a little bit again to this picture, is the fact that you have already established a circuit. So that's kind of given. And the objective is now to somehow share this circuit between multiple users. And this circuit is simply some form of allocation of resources, like the frequencies and something else, and you want to share among the time. So with the frequency division multiplex, you divide in the frequency. So effectively, if you have 4 users, you're saying that the frequency band from x to x plus 1 is dedicated to one user, from x plus 1 to x plus 2 to another user, from x plus 2 to 3 is yet another user. And this is how effectively the communication will happen afterwards. So like one user only transmitting in one specific bandwidth, the other user in different bandwidth, the third user in another bandwidth, and yet another user in yet another bandwidth. So effectively all communication happens, and kind of this all 4 users are happy. But again, this is only 4 users and nothing kind of good is happening. For the time division multiplex, what we can divide, instead of dividing the bandwidth, we can divide time. So effectively we just split the time into slots and allocated slots to different users. So at one point of time one user transmits, and another time of point different user transmits. And you can have multiple subdivisions for the frequencies, and you can have multiple subdivision of time slots, and this can continue. One thing that I want to mention here is this is traditional FDM and TDMs, but what we can have is not fixed allocation for a specific user, but rather have the slots available, and there is some additional mechanisms to allocate specific frequency at specific point of time. So it's we can have a combination of FDM and TDM and some smart allocation of those resources. So some of this effectively in existence today with Wi-Fi, or Wi-Fi, whatever our cellular phones. So we, in all cases, we sharing the same media. We have limited amount of resources of radio, and we're trying to share them in some fashion. So we use an FDM TDM in that sense. But let us think of efficiency of packet switching versus circuit switching, or how, in other words, how inefficient circuit switching is. And so this example is based on sharing the same link by multiple users. And the question here is pretty simple. So given one shared link of 1 megabit per second, that's considered an extremely old link. And we want to share this link by as many users as possible. Yet we want to provide some form of a guarantee for service for each user, and just get some additional element for this task, saying that the users not active all the time, and on average, on a big average, they active only 10% of all allocated time. So the solution for circuit switching is quite simple. So the parameter of 10% of the time simply not going to play any role. So for this circuit switching, the answer is quite simple. You have only limited capacity. You have to provide the service for user. In this case, we need to provide 100 kilobits per second of the service, and that's it. This 10% of time doesn't really play any kind of role, because you cannot do anything with this in circuit switching. So the answer would be simple 10, because we have to divide 1 megabit per second by 100 kilobits per second that we have to provide, and that's it. And this is a reservation. For the packet switching, things are getting a little bit fuzzier, because now we get into the point of the probabilities, because with the 10% of average, we can decide that there is a certain probability that the people not going to be using a channel at the same time. So for example, that given here, with probability that with probability of what it is, more than 99%, we can easily share this link by 35 users, providing this the same amount of quality to each of the users. Again, at this point, we're not going to have the guaranteed 100 kilobits per second, and we're not having it in today's networks, but it's still providing way many users. So with the same number of links, with the same capacity of the link, we actually increased capacity by 3.5 times. And if we play a little bit with probabilities, if we only guarantee 80% of time, then the number of users can increase this much more significantly. And just for the reference, this virtual circuit networks is just trying to imitate the packet switching networks, or trying to imitate the circuit switching networks, but using packet switching. So what they're trying to do is to use packets, but yet provide some form of reservation for the channels. So they still send a packet, but this packet first needs to go through so-called resource reservations, and then only packets destined to the same destination would be allowed to be sent out if there's available resources. And the rest of the capacity of the channel can be shared between normal non-virtual circuit packets. But I'm not actually aware of too much use of this type of technology today. Now, getting back to a little bit, getting to a little bit more complex element of packet switching is their properties. I think I already briefly mentioned in part one that links have quite a bit of properties, and so we're going to be talking a lot more about the delay as a property. But for now, just have some introduction of what we have. So we have the bandwidth of the link. So effectively, it's a width of the pipe, how many things we can pump into the pipe in a moment of time. There's a packet drop, effectively the amount of packet being dropped by whatever reason. And for our existing packet switch networks, we have two interesting things. So first of all, so there is a so-called multiplexing and queuing. So I just give you the idea what is happening. But so the multiplexing is the fact that the router or whatever switch or any other element of the network can receive packets from multiple sources, and yet he needs to send this packet to a single destination. I mean, you can think about this simple hub at your home, or a simple router at your home, where you receive packets from your WAN interface, from the internet interface on the router, and that you send out to different destinations, to different Wi-Fi stations or different Ethernet stations outside. And so that would be multiplexing. Demultiplexing effectively is the other way around, but it's in this sense doesn't really play too much role. And queuing is actually playing the role of the role of queuing is the fact that the link capacities or link bandwidth, I'm sometimes going to be using these terms interchangeably, are not necessarily the same. So if, let's say a hypothetical example. So we have a simple switch, router, or whatever device that has two interfaces that has 1 megabit capacity each, and the outgoing interface is 2 megabit per second capacity each. In that case, there's no queuing of any kind. So you receive the packet, you can put this packet on the outgoing interface. You receive two packets from both interfaces at the same time. You can put both packets at the same time on the outgoing interface, so no problem at all. But if you have a different picture, like for example, as illustrated on the slide, so if you have one inbound 100 megabits per second and outbound is only 1.5 megabit per second, so it's 100 times smaller, then we potentially have a problem. And the problem, well, maybe not a big problem, depending on how much traffic node A is actually pumping to the network. But what we're trying to do is to receive all the packets as we can and try to schedule them for transmission to the outgoing link. So as you can see, illustration here, we receive packets from node A, receive packets from node B, and then putting them into so-called queue. And simply for the outgoing interface, we're just trying to send as many packets as these links can process. And if we're not sending too many packets and our queue is reasonably long enough, or our capacity of our queue is reasonably long enough, we may not even lose any packets. But if we get to the point that our capacity of our buffer or queue is limited and we send in way too many packets, then we're simply not going to have ability to put packets into the queues, and we'll just have to drop them. So this one relates to what I already mentioned in part 1 regarding the congestion. So this kind of the fact that we're trying to send a packet and packet being received by router or switch or some other node, and it doesn't have capacity in this outgoing queue, then we effectively have a form of a congestion. Yeah, already it's actually mentioned on the slide. So that's kind of the basic knowledge of the multiplexing. Multiplexing, we receive packets from multiple interfaces and kind of serializing them one by one for the outgoing interface. And you can think of this router kind of doing multiple multiplexing operations, because if we consider big routers, they have like hundreds of interfaces. They receive traffic from all interfaces at the same time, and they kind of send out packets to multiple different interfaces. So it's kind of multiplexing and demultiplexing at the same time. And when we have a queue, and we always have a queue, we receive the packet, we put the packet into the queue, and we're trying to push packets outside the router, as many as we can from the queue. And you may actually heard the term store and forward. So this is actually reflects what our switches and routers are doing. So they store the packet into the queue, and kind of the interface operates based on that queue that we have, and just sending packets outside. So dealing with the congestion. So I already kind of mentioned this last time. So with computer networks, dealing with congestion is one way. So you simply drop the packets. In real life, you cannot really do that. Like, you cannot afford simply drop the car out of the freeway, or like if car is trying to get to the freeway, you cannot just forget about this car. You have to still deal with this. But in computer networks, we don't provide the guarantee for delivery of each individual packet. Rather, kind of it's application business or transport layer business to figure out what exactly needs to be done with this packet, how to actually deliver the information to this destination if we need to deliver this packet. And for delivery performance, there is three basic parameters. I kind of hinted this already. So the throughput, so this one not necessarily the same as the capacity of the link, because when we're talking about link capacity, this is just for one thing, versus throughput is the overall capacity of each individual path. So effectively, in most cases, it will be the minimum of capacity of individual links. So if we have 3 links connected, one is 100 megabit per second, 2 others 1 megabit per second, then the overall throughput for the end-to-end throughput between client and server would be effectively 1 megabit per second, because you can pump more data through it. Loss rate is a slightly different thing. It's just the number of kind of how many packets have been lost versus number of packets been transmitted. And we're going to talk about what the causes of the loss. And you can, for the calculation purposes, when we're running tools like a ping or some other ones, we estimate based on number of we transmitted packet and number of we actually received packets. But there are different reasons for why packets can be lost. And finally, delay. And for delay, we're going to be talking quite extensively in a few more slides. So for the throughput, just to reiterate, so we have like either throughput between over the single link, so effectively kind of this basically very similar to link capacity. It's either something to point, or if we consider multi-access, so this one, okay, so for the multi-point, it would be literally equivalent to the link bandwidth, because if you're the only user of that link, and therefore you can send as many data through this link as you can. In case of multi-access links, things are slightly different, because you have to share this link between others, either whatever mechanism we can share, like TDM, FDM, or some form of combination of those. And if we consider throughput between 2 end hosts, it will be effectively some minimum of all links that are available in the system. Okay, so now talking about the packet losses. So there's a multiple reasons packets can be lost, and maybe consider several different scenarios. So if we consider wired networks, maybe in old days when kind of signal the technology was not that good, there could be some random errors in the wires. In today's environment, if you consider the just Ethernet wire or some like fiber optics cables, there are no random transmission losses in those cases, and the majority of the losses that happen in those networks are due to the congestion, due to the fact that somebody is pumping at some point more packets into the system, and not enough and there's some links with a smaller capacity, or we simply pump in too many packets at the same time, or like the burst of the packets that the buffers cannot simply support. So this is effectively the reason for the losses. In other link layers, so for example in wireless links specifically, there's a tons of various errors that can happen. So for example, if you turn on the microwave and somehow forgot to to close the door, and somehow microwave is still working, then there will be a lot of transmission losses in that environment, because I mean the microwave will be like interfering with the signal transmissions by the nodes. At the same time, the nodes themselves can transmit at the same time, create various kind of interference between themselves. But this can happen by the nodes within the same, connected to the same Wi-Fi network, or even by nodes connected to different Wi-Fi networks, or nodes running completely different Wi-Fi protocols. So for example, Bluetooth connected device can very easily interfere with Wi-Fi connected devices and kind of create a lot of problems. And plus, kind of the nature of the wireless medium is it doesn't have that good quality, and the farther away you're from from the either access point or the other device, then there is a higher chance that you're actually not going to be able to decode the signal, because the signal have been attenuated too much, and you cannot really decode what you've been receiving. So that's kind of the attribute of the losses, is transmission, which is not that happening in wired links, can happen in wireless links. Congestion, the major part, and in wireless links there's a lot of interference losses. Okay, so now talking about the delay. So we talked about the capacity, bandwidth, this one was packet losses, and finally we got to the delays. So this one is the most complex and yet the most interesting part, because the delay is actually quite complicated. As you can see on the slide, the delay is actually contains multiple elements. So it's a nodal delay, queuing delay, transmission delay, and propagation delay. And let's just talk each delay individually. So nodal delay, or you can also hear as it heard about it as a processing delay. So this one is effectively anything that delays the packet while it's being processed. So if like a router is busy and is trying to look up the routing table, and it's kind of taking a lot of CPU cycles to do that, there will be some nodal processing delay. If packet needs to be checked for kind of very complex checks, I don't know what exactly it could be, then again there's a lot of processing that is involved there, and there is a delay. Good for you, I mean bad for everybody in general that this delay exists, because the capacity of routers, capacity of our computing elements is not infinite, so we have that delay. But good for you for the purpose of this class is that it's not really calculatable, because that really depends on kind of how busy is the host, what is the CPU on the host, what the memory resource, and so forth. So I'm not kind of in any of the exams, I'm not going to be asking that question, yet I will be asking other questions. So now about queuing delay. So queuing delay is interesting. Like if you got kind of idea what the queue is and how the queue is being used in this store and forward systems, it's effectively the time the packet needs to wait in a queue before being transmitted. And assuming we have like a fixed size for the packet, then you can easily calculate this delay by the transmission. I put it as a transmission delay, but effectively it's have a dependency on how fast you can put the packet on a wire, like like depending on the bandwidth of this specific link, and the number of packets in a queue. So that's it. If we have packets of different sizes, then it really kind of, you need to think, kind of calculate the size of all individual packets that needs to be transmitted, and then kind of get to the point of the transmission delay. Maybe if I kind of give you more details about the transmission delay, it will be a little bit clearer. And so the transmission delay is really something that related to the bandwidth of the link. And one thing, so the unit of the okay, maybe it's not in this way. So it really depends on how fast you can put the whole packet on a wire. Normally you cannot put, I mean, there's kind of everything is finite capacity, so we cannot just immediately put the whole packet, like let's say L bits of the packet, on a wire and consider it be done. It really taking some amount of time to actually be transmitted, like actually be encoded on a wire. And you can kind of really estimate this delay based on a link bandwidth. So you cannot pump the packets fast through the link faster than the link bandwidth, and it's kind of can be so that this transmission delay effectively can be estimated by the inverse of the link bandwidth. So you simply take the length of the packet and divide it by the bandwidth. So that would be approximate transmission delay. Yes, kind of it can, so the actual transmission can happen faster and we can have a smaller bandwidth for the link for some reason. So we can send packet and there is some period of time that we don't send the packets at all, but this formula can serve as a pretty good estimation of transmission delay. So the other one, so the propagation delay. So assuming we can put packet on a wire, like just immediately we like just pumping bits into the packet, like encoding in some form, like in modulating them in some form, we still have this thing called the speed of light. So unfortunately nothing happens immediately, and we have, even for the small links, the packet, this electrical signal still have to travel. And even though it's traveling fast, it's still bounded by the speed of light in wireless, and the speed of light in copper and fiber is actually smaller than the speed of light in wireless. So if you get these formulas, you can actually estimate some form of delay depending on the link length. So for the small ones, it would be very, very small links, but if you consider transatlantic links or trans-Pacific links, that delay would be significant. And if you consider links, not links, but rather connections through the geostationary satellites, so those delays are really, really huge. So like they are on order of hundreds of milliseconds, and you can actually estimate those things. And again, getting everything back together, example estimate. Yeah. So if you have just a single link, you can relatively easy estimate all this nodal queuing, transmission, and propagation delay. And I'm giving you all these formulas here. So assuming, so in this case, I'm having the link bandwidth. Yeah. So the just basic assumption here is that you only transmitting packets and incoming and outgoing links are the same bandwidth. So nodal processing, as I said, we cannot really estimate. Queuing delay, in the case if there is no queuing happening, so in, let's say, the bandwidth of incoming links is overall less than bandwidth of outgoing links, then in this case there's no queuing, so you can just assume 0 in this case. So for the transmission delay, you literally need to calculate based on a link bandwidth. So what is happening, so you have, if you have a packet of 1000 bits, and if in bytes it would be divided by 8, you kind of divide by bandwidth, which is 1 megabit per second, and you get around 1 millisecond that it's actually taking to put a single packet on a wire. So just to kind of put, like, it's not really you kind of depending on how the packet is encoded, like on a link layer and a physical layer. It's not necessarily that one bit at a time being encoded. But you can kind of approximate your thinking, just thinking that each bit taking some specific amount of time to be encoded and put on a wire, and that's effectively the until all the bits being put on a wire. This is the transmission delay. So we have 1 millisecond to put 1000 of bits on a wire. Finally, the propagation delay would really depends on link length, and if you consider this 100 kilometers. Okay, it's not in miles, but in kilometers. So you can easily calculate it based on parameters I gave you, like for the fiber link of 100 kilometers, this would be 0.5 milliseconds. Okay, so the example is a little bit silly. I don't know what kind of fiber optics is 1 megabits per second today, but just for the purposes of this example, there is one huge 1 millisecond delay for the just transmit the packet, the single packet, and there is a 0.5 milliseconds to actually move this packet from the switch A to switch B physically, due to speed of light constraints. And if you consider total delay, so this would be bounded by this 1.5 milliseconds. So it can be more if we have some delays on during the processing, that would be effectively more. If you have some incoming links or like somebody is sending a lot of traffic, then of course that'd be also more. Things when we have multiple kind of links are getting a little bit more complex, because we have to actually consider different capacity of the links. There is multiple queuing happening, even though they may not be happening kind of one by one. But let us get to the example. So in this case, we're trying to send 8000 bits packet, so it's just 1000 bytes in a packet. For the bandwidth of 2 megabits per second, we're going to ignore for the purpose of the propagation delay, and because propagation delay is technically quite simple, it always be the propagation delay of all links. So because the packet has to travel between this point and this point, this point, this point, and this point, and that point. Okay, so for the multiple links, so the picture becomes a little bit more complicated. So this one is actually a simple example, and this is simple example, and the example is simple here just because the all bandwidth of all links are the same. So, and there's only one connection from each host to kind of the next host. So in this case, whenever we send in the packet, the only thing that, how many packets we send in here doesn't really matter, because every time we send a packet, it will be immediately sent out on the next link and the next link and the next link. So effectively, the time we need to spend to actually deliver this packet to the destination would be based on transmission delays. Assuming there's a very small propagation delay, if, like, for example, some lab environment. So in this case, like, you can completely ignore the propagation delay. So what we're going to have is, because this node will have to spend an amount of time to put this packet on a wire, then the first router will have to spend this amount of time to put packet on a wire, and finally the next node also will need to spend time to put packet on a wire. And effectively you're going to get, if you calculate all this correctly, around 12 milliseconds that this packet actually need to spend inside the network to be transferred. So we can play with the Caravan analogy that kind of represent the same thing as the routers. It's just asking question in slightly different way and slightly different definitions of the bandwidth. So let's say we have this bandwidth of 100 kilometers an hour as our road capacity, and the same as traveling speed of the car, and there's a toll booth. So for example, and toll booth is acting as some kind of queuing element. And if we consider that it takes around 12 seconds to service a car, and if we had a question how long it would be until the car would line up before the second toll booth, we would estimate 62 minutes. Because there's a time to push entire caravan through the toll booth onto the highway. So it's effectively each car will have to spend this 12 seconds multiplied by 10 through the toll booth. So that's the amount of time would be required, and the actual amount of time the car needs to travel from one point to another. So that's kind of would be propagation delay in terms of the packet switching. Finally, we get to the point of sending multiple packets in a network scenario. So this one will be almost exactly as this Caravan analogy that we just talked about, but just let's consider our example and what the things are going to happen in this example. And we're considering here is again our 1000 byte packet with 2 megabits per second of the link, and we're going to ignore propagation delay for now because it's very short links. So what's going to happen kind of in this scenario is that the node 1 will create 5 packets at the same time, and this is kind of quite common because the application can create packets way faster than you can transfer through the network. So what's going to happen, all these 5 packets that have been created, they immediately got into the queue. So this can happen fairly quickly. And you can already remember that each packet will have to wait its own turn into the queue to be delivered onto the link. And if we consider it, we can consider the single link first, that this packet will be transmitted. So we'll have to wait at least L divided by B, like if we completely ignoring the propagation delay, for the first packet to be transmitted. And at this point, this packet will arrive at B, it will be queued, and potentially be ready to be sent out further. So at the next point of time, as soon as the packet 1 have been transmitted, now kind of original node A, sorry, there is no node A, but the original computer now is ready to transmit the packet number 2. At the same time, the router, the first router, is also ready to transmit packet 1 that he has received. So now at the kind of time point of 2L divided by B, we're going to have 2 packets moved further. And kind of our transmitting node is ready to transmit a packet again. And kind of if I consider the next time moment, what's going to happen is kind of router 2, router 1, and the node have all been transmitting packets. So it will be packet 1 transmitted by node 2, packet 2 transmitted by router 1, packet 3 transmitted by by the first node. And so kind of we have a situation when we have at each node there are different packets. And finally we're going to have a kind of at the time 4 divided by L divided by B, or 4L divided by B, we're going to have 2 packets received by the end host, and that's kind of you can follow this simple animation. So at some point, hopefully, so at the time moment of 7L divided by B, all packets have been effectively received by the end node. So let me try to contrast this example with the example I just showed you with just single packet that have been transmitted over the same 3 links. Oops, I missed this one. So in this case, we have calculated this packet has to be transmitted 1 by 1 by each node, and we calculated this 3 multiplied by L divided by B. So because we sending packets 3 times by different nodes. In the other case, when we send in 5 packets, we didn't get 5 multiplied by 3 multiplied by L divided by 5. Rather, because we have this queuing, because everything is happening at the same time, we actually amortize some of the cost. So the overall cost was only 5 packets. This is the amount of you have to transmit anyways. I mean, this amount of time you have to spend on putting all this data into the wire, plus only 2 additional things. So, and those 2 additional things effectively were introduced by additional links that we have to transmit the packet. And the rest was effectively, all the rest of the process was pipelined, and everything was quite fairly quick. So this one was a simple example, and the example is simple by the fact that all bandwidths are the same. If bandwidths are different, then we're going to have a slightly different picture. I don't have an example because that would be part of your next homework, or at least one of the homeworks, where you have to calculate how fast or like when you're going to receive packets if you have different capacities of the links. Because if, for example, the capacity of this link was twice as smaller than B, then it would take twice as long to send or put the packet 1 into the wire compared to receiving packets on this wire. And therefore the queue will build up somewhere here, and there will be additional time to transmit a packet. So we wouldn't have the 7L divided by B in that case, but that should be also easily to calculate. So finally, I'm moving a little bit forward to slightly different definition, which is quite related to delays. So delay is effectively one-way thing. So it's from sending one packet or multiple packets from one host to another host. Unfortunately or fortunately, it's not that really to estimate this capacity, because in both ends you have to have a synchronized clocks, and you have to do some kind of very complex calculations. What we easily can do is actually estimate the round trip time. And the round trip time, or it's kind of sometimes referred as a network latency, because it's kind of easy to calculate element, is effectively the time to send packet and receive some kind of a reply. In a simplest case, this would be kind of the same delay multiplied by 2, but it's actually not really the case in many cases. So delay in one way not necessarily equals delay on in other direction, and for a couple of reasons. First, there could be different queues build up in different directions. Links not necessarily the same in 2 directions. So if you remember, or if you know already by some chance, for example, our LTE on the mobile phones don't have the same capacity in both directions. So for the download you have much bigger capacity than for the upload, and the same thing applies for cable modems. So for example, if you have a Comcast or any like Time Warner or whatever provider that using the cable technology and the cable modems, or even DSL, so they are configured by definition to have a downlink capacity much bigger than uplink. And there you have a simple assumption, is that you are more interested in getting information than sharing the information. Maybe not true in everybody's case, but that's what kind of the system is being designed for. So like they assume that you're going to be watching a lot of Netflix and a lot of other YouTube videos, versus you're not going to be uploading a lot of those videos. So that's in one element, and as we're going to be talking way more in the module 3, or like I'm sorry, I think it's module 5 when we're going to be talking about the networking. The paths between nodes in the network are really not symmetric. So this is the property of IP network, where we have a very asymmetric network, and as a kind of estimation. And we're going to take a look at what real paths and what real delays exist in the network. I already showed you the traceroute command in the part 1, And in this part, and I hope you're going to be spending some time to actually playing with the traceroute command, is to actually try to understand what kind of paths are on the internet. So one thing I can tell you, like for sure, that the number of different routers that needed between 2 points on the internet is definitely less 255. That's because the protocol have this limitation. So in IP protocol, you cannot have more than 255 hops, like routers in the middle. But that's kind of the protocol definition. The real number of hops is way less than that. I can give you like a random number of around 15, 20, but again, this is just out of blue, and I will just ask you to at least try to find out the most like number of hops to the destination, to some farther destination. Like just pick something far away you think is far away, and try to use a traceroute command to find out how many hops. And so this one, please post to the discussion forum, because this would be counted as class participation credit. So just I'll show you a little bit more in the next slide what exactly I'm expecting you to do, but try to do that like exercise, like figure out some destinations that you think are far away and try to figure out how many hops are between them. And in addition to estimating number of hops between, like how many routers in between, we can also see how far away things are. Well, no, at least not exactly see, but rather estimate how far things are. And sometimes it works, sometimes it's not, but it's at least an interesting exercise for the lower bound or upper bound. Let me think about. Yeah, like I mean, you cannot go faster than the speed of light, so you can estimate the upper bound, how far away this thing, like the next hop, could have been. Okay, that's not so interesting. So this is what I did, and this is what I'm asking you to do. So simply figure out some domain names that correspond to some host on the internet, and try to have a trace route to them. So you can find something in China, something in maybe Bangladesh, or something. If you can figure out any host in Antarctica or Antarctic, then that would be also cool to see what kind of connectivity they have there, or like how they go there. But in this case, what I'm showing here is I did a simple trace route to one of the google.com servers, and what I got is from my office to the first google.com server was only 9 hops, and some of them you can actually kind of extract some information from the output. So some of them were related to FIU, some of them kind of you cannot really guess what exactly is happening, so they didn't disclose the information. But in your case, if you run the command, it may show you more additional information, especially if you go in somewhere internationally. It usually shows up like it's either airport code or some other designation of the city or some other things from which you can actually estimate where things are physically. But in addition to kind of seeing this number of hops, as I said, it also estimates the round-trip delay. So the round-trip delay for the ping command, if you saw it in the previous part, there was only kind of different ping different millisecond values for the same host. In this case, we have kind of 3 values for the same host, and just for different hosts as we go along the path of the internet. And as you can see, the time is actually increasing because it's taking less time to go to the first hop, then going 2 hops, then going 3 hops, and so forth and so on. Okay, so before I go forward, I actually want to show you a few more examples in addition to lectures. So what I want to just to show you like how you can do things. So for example, let us pick some random example, and I'm trying to think of what kind of data center we can pick. Google is kind of obvious case, but it's not so interesting because there are too many data centers of Google. So what I can try to do is okay, I know some host in Russia, so I'll pick that one. So let me ping it first. So there's a ya.ru, and if we ping, it will give us some result. So as you can see, just trying pinging, and giving just some information about the TTLs and information about the timing. So as you can see, the timing here is 147 milliseconds. And kind of task for you, this is kind of task as part of the same task that I'm asking you to do, the trace route. Just tell me approximately how far away this host could be. So it could be closer than this amount time that estimated, like distance estimated by the time, and considering just normal speed of light propagation. But how far away this thing can be. And if I change the trace route to ping to the trace route, so now I'm gonna see quite a different thing. Let us wait a little bit, and it will try to give us some information. So as you already see, not always you can actually get this information. So in some cases, the host responded positively that it was somewhere on the path to the destination. And in this case, it responded it was somewhere in Miami, Seabourn, and it responded, and then there is nothingness. So it just simply means that this router is not configured to respond to those packets. So simply it probably drop in those packets for whatever reason it wants to do that. But eventually, it's if host itself or router before the host actually responds to these packets, it may recover. Not necessarily, but it may recover. And if you play with the kind of different domain names, different IP addresses, you may be able to find different results. So in this case, it happened to get back to resolve something, and in this case, we could see that it reached some router in Washington. And kind of you see significant increase in round trip time, which was 28 milliseconds, and you kind of guess that it's based on distance from Miami to Washington. And finally, when we got to the next point, it's somehow just one hop from this Washington place to final destination. The time jumped by more than 100 milliseconds. So effectively, I can tell you what I'm estimating what have happened. So in this case, it's most likely there was a transatlantic link to Russia somewhere, and in that case, it just was directly connected to the data center that served this website. There's probably some more complex infrastructure inside, and we'll learn how exactly it may have worked inside. But at least on the surface, it was kind of directly connected to the link on the other side of the Atlantic. And again, try to play with different IP addresses, different host names. You can either try to come up with some random innovative host name, or you can simply just try to ping some random IP address. So I suggest you try to ping it first to see whether it's actually response or not. If a response is short enough, it may be not interesting because it's somewhere in the United States. If it's something far away, like I just randomly pick this number. So it got to some point. As you may notice, I accidentally put -n, and this -n simply prevented me to resolve these IP addresses to the host names. How exactly it's happening, we also learn, and this is going to be in module 3. And hopefully it will get to some point, who knows. But we already see that the delay has increased from 0, like a few hops away from ourselves. So we know that it went to Miami somewhere, Miami data center. This one, Ashburn, I guess it's going somewhere there. And then I don't even know what it is. I can only guess it's going to the Amsterdam for some reason, based on AMS and NL and the amount of time it actually need to go from this place to that place. But again, this is only my guess, and there's additional things that are happening with protocols with the lower layer protocols that are not visible in networking layer, that not necessarily making these numbers correct. But what I wanted you to play with is to just trying to see what you can infer from these numbers. Like, first of all, how you can get these numbers to estimate the network structure, and how you can get the numbers. So this one thing, and another challenge that I would like you to do is to so if you're local, try to get some trace route to FIU.edu from home, and then try to do the same from FIU network. Because what I want to kind of get from that is the path from FIU to your home network would most likely be significantly different from the path from your home to FIU network. So the one that the trace route shows you in one direction and the other direction most likely will be different. But I'll give that opportunity for you to explore. And so what I want you to submit as a kind of item on the discussion forum is several trace routes, like effectively just copy paste of whatever I just did, plus a little bit of explanation of what you kind of estimated have happened. If your trace route included, as you estimated, some transatlantic, transpacific links, just indicate where you think those links between which hop and which hop, and just give me rough estimation on upper bound of the distance of that link, like how far away that link could have been. This kind of not precise knowledge, but at least some potential information that you can extract. So this is effectively all I wanted you to learn as part of this module. This is just additional information for what I just said, for what we just playing with. You can play with this IP address. I forgot why exactly I picked this one. I think it was also some kind of random address somewhere far away. And what kind of to summarize what we have learned in this part is a few things. So one thing is network sharing methods. Look, if we have a network that consists of multiple different links, multiple different places where you can connect those links, you can have several ways of sharing those resources. You can do it in a guaranteed way. You can do it in less guaranteed way. So in a guaranteed way, you have to do some form of circuit switching. So you kind of send a request. Like if you remember, there were like dialed phone numbers or dialed phones. We're kind of actually doing things. So in those cases, there were like actual physical circuits that connected you to, at each point of this routing, they connected to a different specific circuit. Or with packet switching networks, you don't do any kind of reservation, and you kind of packets are being either processed if there is enough capacity, or being dropped because there is not enough place in the queue, or dropped for whatever other reason. You learn the properties of the network, properties of the links, like link bandwidth, what else? Link capacity, link delay, bus rate. We also talked a lot about the different types of delays, and I hope you got some idea of how to calculate the processing, queuing, and propagation delays, because this is, even though it's quite a simple topic, I still want you to get a very good hold of it, and we can have a few exercises on kind of how to calculate those things. I gave you a few examples of how to calculate things using the links of the same capacity, but try to play with the kind of at home with the links of different capacities. I'm never going to ask you very complex questions, but I may include some questions that include the links that are twice as bigger capacity or twice as smaller capacity. And finally, the cumulative delays on the internet is cumulative delays on a host can be estimated as the sum of all delays, and I just showed you the tools how you can estimate real delays on the internet. Again, those are not precise science because there's a lot of estimation involved, but it's a very interesting thing to have. Okay, so thank you for listening this part, and I hope to see you soon.